Hello everyone. Today we are presenting on the topic information spread and diffusion models in networks. The topic is highly relevant in business analytics because modern businesses operate in highly connected ecosystems where information does not move randomly, it follows patterns that can analyze and optimized. Our objective today is to understand how information propagates across networks, the mathematical model behind it, and also how organizations leverages those models for decision making, marketing, and risk analysis. I am Kanish Khan, along with my partner Nandigam Pirkat. We will guide you through both the theoretical foundations and practical applications. Let's begin with the course concept. What is information diffusion? At its core, information diffusion refers at how information, ideas, behaviors, or innovations spread across a network over time, very similar to how a contagion spreads in epidemiology. As shown in our slide, this process is structured using four key components. First node, it will represent entities such as individuals, organizations, or systems within the network. Second, edges, those defines the relationships or connections between the nodes such as friendships, transactions, or communication links. Third, seed nodes, those are the initial starting points of diffusion, which forms the business perspective. Those are often influences or early adapters. And finally, cascades, which represent chain reactions, which one activation triggers multiple subsequent activations. Now, from a business analytics standpoint, diffusion is extremely valuable. As highlighted on the right side of the slide, it helps in the predicting virality, such as forecasting whether a product will go viral or not. It enables targeted marketing, reducing cost with maximizing each reach. It allows us to analyze opinion influence, especially in social networks, and it helps map knowledge flow within the organizations, identifying bottlenecks or silos. The key takeaway here is diffusion is not random, it is governed by both the structure of the network and the behavior of individual nodes. Types of network. Now, to understand diffusion properly, we must analyze the structure of the network because structure directly determines how fast and how far information spreads. As shown in the diagrams on page 3, there are four major network types. First, scale-free networks. Those networks follows a power law distribution where a small number of nodes called hubs have extremely high connectivity. For example, on platforms like Twitter or Instagram, a tiny percentage of users generate the majority of content spread. From a business perspective, those hubs are critical because activating them leads to maximum impact with minimal effect. Second, small value networks. Those networks exhibit high clustering but also short path lengths, meaning any two nodes are connected through very few steps. This explains the 6 degrees of separation concept. Those structures are common in LinkedIn and organizational networks. Third, random networks. Here connections are formed randomly with equal probability. Diffusion in such networks is more uniform but less efficient compared to scale-free networks. 4. Regular or lattice networks. Every node has the same number of connections, resulting in slow and predictable diffusions. Those are often seen in structured systems like supply chains or sensor grids. The critical business insight is network topology directly impacts diffusion efficiency. Among all, scale-free networks are the most powerful for rapid spread due to hub dominance. Next, SI model. Now we move into the mathematical modeling of diffusion, starting with the SI model. Susceptible and infected as shown on page 4. This is the simplest diffusion model where each node can exist only in only two states. Susceptible, susceptible, which means not yet influenced. Infected as adopted the information permanently. The governing equations defines how quickly nodes transmitted from S to I, controlled by the parameter beta, which represents the transition rate. The diffusion pattern follows an S curve, which is very important in business. Initial slow growth, rapid expansion phase, final saturation phase. Eventually, the system reduces full saturation, meaning all nodes become infected. From a business perspective, this model represents irreversible adoption scenarios. For example, when customers permanently switch to a platforms like a payment app or subscription services. However, the limitations as clearly mentioned in the slide, is that this model assumes no recovery, which is unrealistic in many real world situations. This leads us to more advanced models. Next, SIS models, SIS and SIR models. To address the limitations of the SI models, we introduce recovery into system resulting into the SIS and SIR models, as shown in the slides. First, the SIS model. Nodes move from susceptible to infected and back to susceptible. This means reinfection is possible. This model is ideal for cyclical or recurring trends such as seasonal fashion, recurring news cycles, marketing campaigns that repeat over time. The system stabilizes at what we call an endemic equilibrium, where the information never fully disappears. A key metric here is R naught. If R naught higher than 1, then the spread sustains. If R naught lesser than 1, the spread dies out. Next is the SIR model. Nodes from susceptible moves to infected and then moves to recovered. Recovered node gain immunity and cannot be influenced again. This model represents one-time viral events such as product launches, breaking news, viral campaigns. The spread grows, peaks, and then declines, forming a natural life cycle. The key insight from the comparison table in the slide is SI, which will make permanent adoption. SIS is recurring trends. SIR is one-time diffusion. Together, those models from the core theoretical slides foundation of diffusion modeling. Next, independent cascadal model. Now we move to more realistic and widely used model, the independent cascadal model. Unlike previous models, this is a probabilistic model. The core idea is when a node becomes active, it gets only one chance to activate each neighbor. The success depends on a probability value assigned to each connection. The diffusion process follows those steps. Select initial seeds attempt to activate neighbors. Newly activated nodes continue the process. The cascade stops when no new activation occurs. Now, from a mathematical perspective, the model has three key properties. Stochastic outcomes vary across runs. Submodular dimensioning the returns when adding more seeds. Approximate greedy algorithms achieve 63% of optimal spread. From a business analytics standpoint, this model is extremely powerful. It directly answers a critical question: which set of users should we target to maximize the total reach? Companies stimulate thousands of scenarios as mentioned in the slide using techniques like Monte Carlo simulation to estimate expected diffusion before investing in campaigns. This is the foundations of data-driven influencer marketing and viral campaign optimization. With this, I hand over to my partner for the next sections.
Alright, so my friend just walked you through the independent cascade model. I am Prakyat and I will be taking you through the second half of this presentation. Now the IC model assumes one message, one shot, that's enough to potentially activate someone. But think about your own behavior for a second. When your own company rolls out a new software like Notion or Slack, do you immediately start using it because one colleague mentions it? Probably not. You wait until 3 or 4 people around you are already using it. That's the linear threshold model. Every node has a potential threshold. Its resistance to change it only activates when enough of its neighbors have already activated. It's cumulative peer pressure, not a single nudge. The key insight here: high threshold nodes, the skeptical senior managers are often the most well connected once they finally cross the threshold. Their activation unlocks a massive downstream cascade. Business applications, enterprise rollouts, organizational change management, where your target gatekeeper manages first, and predicting when a technology cross from early adopters to the mainstream. So now we understand two ways of information spread: through individual chance with IC and through collective peer pressures with LT. But but both models raise the same critical question: which nodes do we actually seed? That's the influence maximum problem. Now the big question every business wants answered. Given a limited budget, which people do I need seed first to get maximum spread? Imagine you are launching a fitness app and can only give free subscriptions to 10 people. Which 10, if they post about it, will create bigger cascade of signups? Finding the perfect answer means checking every possible combination of 10 nodes. from off a 10 million users, computational impossible. The problem is NP hard. The breakthrough came from Camp Kleinberg and Trados in 2003. They provided the influence spread function in submodder. The more seeds you already picked, the less value each extra seed adds. Like how hiring your first employee adds more value than hiring your 100th. Because of this, a simple greedy algorithm, just pick the best node at each step, is guaranteed to get you within 63% of a true optimal. That's provable, not a guess. Three algorithms made this scalable in production. CELF, which is 700 times faster than basic greedy. IMM, which channels networks with billions of nodes. And TIM plus, which achieves near linear time with probable guarantee. This is exactly how brands decide which influencers to invest in before communicating campaign budget. The greedy algorithms gives us a 63% guarantee, but running even one simulation is expensive. So in practice, before we run any algorithm, we use centrality metrics to shortlist the most promising candidates. Think of it as the filtering step before the heavy computation. Before running expensive simulations, we use centrality matrices to shortlist the most promising seeds candidate. There are four types. Degree centrality, simply the number of direct connections a node has. A celebrity with 10 million followers has high degree centrality, broad immediate reach in one step. Between a centrality, how often a node sits on the shortest path between others. Think of a journalist covering both tech and healthcare. Most tech people don't follow healthcare people and vice versa. But this journalist bridges both worlds. When they share something, it crosses community boundaries that would otherwise never interact. That's high betweenness centrality, and it's the most powerful metric for diffusion. And closeness centrality, how quickly a node can reach everyone else, like a central project manager with open channels to every team. When they broadcast something, the whole organization hear it first. And eigenvector centrality, you are influenced if your connections are influential. This is the foundations of Google original PageRank algorithm. The critical takeaway is companies that picks influencers purely on follower count consistently underperform network ever selection by 2 to 8 times. The best seeds combine high degree for immediate reaches with high betweenness for cross community and spread. So we now have the full toolkit, the models, the algorithms, and the metrics to identify the right seeds. Let's see where all this actually creates measurable value in the real world. So where does all of this actually creates business value? Five domains quickly. Viral marketing. Brands run IC model simulations before committing influencer budgets, so they know how the expected reach before spending a rupee. Churn propagation. Negative sentiments spreads like a contagion through customer networks. Telecom companies use SAR based models to catch the early signals and intervenes before an entire cluster churnouts. Organizational knowledge diffusion. Companies map internal communication network to find where expertise gets trapped and who's the bottleneck employees are. Betweenness centrality makes those invisible blockers visible. Financial contagion. The 2008 crisis was a diffusion cascade. One institution failed and triggered defaults across the whole banking network. Base 3 now mandates network aware stress testing for large bank because of exactly this. And supply chain disruption. The IC model traces how a single supplier failure propagates downstream, which became critical during the global semiconductor shortage. Same models, five completely different industries. That's the power of this framework. Out of all those applications, viral marketing is one of the with a high clearest before and after numbers. So let me walk you through the actual campaign that ran these exact methods and the results were hard to believe at first. Let me bring everything together with a real case study. A customer brand is running a product awareness campaign on Twitter. Budget allows seeding only 10 influencer accounts across a network of 5 lakh users and 4 million follower connections. The obvious move is pick the 10 most followed accounts. Most brands do exactly that. Instead, the data team built the full follower graph, estimated retweet probabilities from 6 months of historical data, and ran the CELF greedy algorithm under the IC model to find the true optimal 10. The results: random selection is 12,000 users reached, top 10 by follower count reached to 45,000 users reached, and IC model optimal reached to 98,000 users. That's 8 times the reach at exactly the same cost. The critical finding: the optimal accounts were not the most followed, they were bridge nodes with high betweenness and centrality. Accounts connecting multiple sub communities that would otherwise never interact. Think of it this way: the most followed accounts had millions of followers, but those followers all lived in the same bubble. A bridge node plants your message at a crossroads, not insights on town. Top 1% by between a centrality drove by 60% of the total cascade. That's the single most important practical lesson from everything we have covered. That 8 into result is complete compiling, but it's almost important to be honest about where this model still falls short. No tool is perfect, and diffusion modeling has some real open knowledge, open problems worth knowing. Before we close, let's be honest about where this model still falls short. First one is computational scalability, where influential maximization is NP hard. Even with CELF and IMM, evaluating one seed set needs thousands of montochorial runs. Scaling to billions of nodes is still an unsolved research problem. And second one is parameter estimation. Beta and theta are not directly observable. You infer them from historic data, which introduces significant error. Coming to third one, dynamic networks. Real networks change every second. Users join, leave, block each other. Standard models assume a static snapshot and miss that entirely. And fourth one, the misinformation problem. A landmark MIT study in Science found false to spreads 6 times faster than verified information on Twitter. Credibility aware diffusion models are not a standard practice. And finally, ethics. The same algorithm that power viral marketing can be weaponized for propaganda and political manipulation. To wrap up, we covered the LT model influence maximization with its 63% greedy guarantee. CELF, IMM, and TIM plus algorithms, centrality matrices, 5 business applications, and a case study showing 18 to reach from the same budget. The next frontier is graph natural networks, learning transformation patterns directly from real world data without needing handcrafted probability parameters. And we'll leave you with this: network position matters more than individual attributes. The right seeds, not the loudest voices, determine the outcome of a diffusion cascade. Thank you.